Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our fourth and final lecture covering material from Chapter 6. We begin this lecture with a brief summary of the quantum numbers n and l. These were covered in the previous lecture. We learned in the previous lecture how to use our periodic table to determine the shape of the orbital holding the outermost electron for any element. Pause this video and try to absorb all that's going on in this slide. The next quantum number is called m sub l, and technically it's called the magnetic quantum number, but I like to think of it as the number of spatial arrangements. We determine m sub l from our L value. M sub l values range from negative L to positive L, including 0. So what I mean is, if we took an S-block element where the orbital shape is a sphere and L equals 0, our m sub L can only be 0, which means there is only one spatial arrangement for a sphere. And this makes sense, because if we were to hold a spherical shaped object like a basketball, we would be able to rotate it in any direction and we still have that same spherical shape. When L equals 1, we have three spatial arrangements, or we could say m sub L equals -1, 0, or +1. I like to think of this in terms of an XYZ axis. Since L equals 1, our orbital is dumbbell shaped. See in the upper left how the dumbbell can exist along the x-axis, the y-axis, or the z-axis? This is why there are three p orbitals. For a d-block element, our L value is 2. This means that m sub L can equal -2, -1, 0, 1, or 2. In other words, there are 5 possible spatial arrangements, which explain why there are 5 possible d orbitals. Remember, each of these orbitals can hold 2 electrons. As stated in the previous lecture, the quantum numbers provide an address for each electron. Since each orbital can hold 2 electrons, we differentiate these 2 electrons using the final quantum number m sub s. We use the term spin, and there are only 2 values, -1/2 and +1/2. So within a full orbital, the only difference in the quantum numbers between the 2 electrons will be the spin. This drawing attempts to put all of the quantum numbers together to draw the overlapping electron clouds. For n equals 1, there is only one orbital. This is spherical in shape and holds 2 electrons. For n equals 2, we have an s orbital that also holds 2 electrons, in addition to the p orbitals. L equals 1 for p orbitals, and m sub L tells us there are 3 orbitals in total. We can call these -1, 0, +1. The 3 orbitals all have a dumbbell shape, but there are 3 different orientations of this shape, 2 of which are drawn. This image was taken from your text, and it may serve as a study guide. I will encourage you to become very familiar using the periodic table for determining the quantum numbers, since you'll always be provided a periodic table for any exam. This slide provides a brief summary of the orbitals and the relationship to quantum numbers. The final topic for Chapter 6 is the term node. A node is a region where electrons do not exist. This evolves from the wave nature of an electron and is described in greater detail in your textbook. What I want to focus in on is the 2 types of nodes, which are spherical and planar, and some simple formulas for determining the number of nodes. The number of planar nodes are equal to the L value, so a spherical orbital with an L value of 0 has 0 planar nodes. These regions look like a piece of paper, and there is one planar node in the dumbbell-shaped orbital because L equals 1. The spherical nodes, sometimes called radial nodes, can be imagined as a soap bubble where no electrons exist. The number of radial nodes is n minus L minus 1. This formula can be used to find the number of spherical nodes and also has applications for determining the n value. We can always figure out the L value from the shape. This image shows the nodes present in the 2s and 3s orbitals. For the 3s, we can use the formula 3 minus 0 minus 1 to realize there must be 2 nodes present. If we can count the nodes, we can use the formula to determine the n value for that orbital. This image shows the planar node that exists for the dumbbell-shaped orbital. Closer to the bottom, I attempted to draw the 2 planar nodes that exist for a cloverleaf-shaped orbital. In summary, the quantum numbers provide the address or location for an electron with nodes if applicable. Next, we're going to study the electron configurations for atoms and ions, which will provide the location of every electron for that atom. A solid foundation of the quantum numbers will be very useful, so before moving forward, make sure that you can assign quantum numbers to the outermost electron of any element. Also, be well versed in the L value and their corresponding letters and shapes. Mark your periodic table with the S block, P block, D block, and F block, and know the shape of each. Thanks for watching. Please give the video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.